Hello everybody. Today we shall start discussions on classical electrodynamics. Now, first assumption is that you already know about classical electrodynamics a little bit, or quite fair enough, I would say. You are already familiar with the Maxwell's equations, and the idea is here to tell you a little more about the Maxwell's equations, the consequence of the Maxwell's equations, and their solutions. So that is the goal of this course. But let us backtrack a little bit, and today is the first class, so probably we'll discuss things which you may already know. Nevertheless, let's start. In electrodynamics, we are essentially trying to find many things. Initially, it would be to find the trajectory of a particle which is charged. So one goal can be to find the trajectory of a charged particle. Now, how do you do it? Well, we combine mechanics with the dynamics. What do I mean by that? Well, mechanics, the laws of mechanics tells us that the force that is exerted on the particle is supposed to be the mass of the particle times the acceleration. And in case of electrodynamics, this force is given if you know the charge of the particle, the electric field everywhere in space where the particle is, the velocity of the particle at that instance, and the magnetic field everywhere in the space. So that's your Lorentz force law. So that you put in here, but then you ask the question, how do I get E and B? That is answered through dynamics, which is a set of 4 equations we call Maxwell's equations. Well, they are not actually a set of 4 equations, but more on that we'll discuss later. So that is the entire program of finding the trajectory of a charged particle. But then you realize that the Maxwell's equations are like some derivatives, types of derivatives of E and B in the left hand side, and I can write it this way, and in the right hand side I have charges and currents. And you will agree that both charge and current will essentially come from the trajectory of all the charged particles that is there in the universe. So it's a closed problem, such that you need to know the trajectory of the charge and current to get the electric field and the magnetic field, and then you put that back in this Lorentz force law, and then you use the Newton's law of motion essentially to find the trajectory. So the entire problem better has to be solved together, and that is something that we learn in the second part of this course. This should be written in terms of a single problem, and what you have learned so far about analytical mechanics this entire problem of electrodynamics, including the mechanics part, should be given by a single Lagrangian. And we will learn how to do that in the later part of this course. There is one more thing that one like to do, and that is that to find the dynamics of the field itself. Turns out that both E and B are function of time also, and because of that they have a dynamics, and that dynamics, if even if there is no charge or current, if you have set in that dynamics, that also has some interesting properties, and sometimes you would just like to study that. Obviously you know what they are called. The dynamics is essentially the electromagnetic wave. Well, with that much of introduction, so these are the two problems that one like to solve in classical electrodynamics. Let us now look at the Maxwell's equations once and discuss a little bit about them. Discuss what they can do, what they cannot do, what they are not, everything. So let me write the Maxwell's equations here more carefully. These equations you are not allowed to forget. Once you have committed to do research in physics, you are never allowed to forget this equation. These are usually referred to as Maxwell's equations in free space. But if you are talking about electrodynamics only, or sorry, if you are talking about classical electrodynamics only, these equations are valid everywhere. So even inside a material. Okay, so that's a very strong statement. Along this, I also like to tell you that this E and B that you write down this equation of, they are, so E and B are the things that you are supposed to find out from these equations. They are function of both space and time. E is a function of x and t, x are all space. B is also a function of x and t, x is all space, t is time. So each of them are function of four variables. So they are, in language of physics, they're also called fields. That's why electric and magnetic fields. And these are the more fundamental quantities, not the H and the D. And that is if you are believing classical electrodynamics. If you try to look at the electrodynamics from the quantum perspective, then your interpretations may change. But for classical electrodynamics, E and B are the most fundamental things, and these four equations, these four Maxwell's equations, are valid absolutely everywhere. Okay. Now let us discuss a few things about this. First of all, we realize that, so let me write them down here point by point. First of all, we realize that these are partial differential equations. Right? So if they are partial differential equations, what is the form of the partial differential equations? The partial differential equations have these forms: operator in the left hand side, on operating on the fields, and the right hand side I have what I call source. Okay, so let us look at this. Let us look at one of the equation, then it will be clear. So like for example, so this is an example. So I have divergence of E equals rho by epsilon naught. So rho is the source. Similarly, I can write the other example, which is curl of B minus mu 0 epsilon naught del E del T. So that is operator on field, but different operators operating on different fields. On the right hand side you have mu 0 J. Right? So this has this form. So I have sources which are external quantities. So rho and J both depends on, again, x, all x and t. And they has to be given to you to solve these equations. Well, these two cases where the right hand side the source is non-zero, they are called inhomogeneous equations. On the other hand, I have other two examples where you write divergence of B equals 0 and curl of E minus del B del T, plus del B del T equals 0. You see here there is no source term. There are some operators operating on the fields in the left hand side. On the right hand side there is no source term. So these are called homogeneous equations. You will see that they actually have different mathematical structures, where in the second part of the course you'll see that these equations are fundamentally different from the first two equations, but that will come later in the course. But all the equations have this structure. Now once it has this structure, then what do I need to solve them? So I need two things. One is rho as a function of x and t, and j as a function of x and t. So that's 3 j's, because j is a vector. This has to be given. And the second thing is the boundary conditions. Right? Now, it is not that only their partial differential equations, the second most important point for the classical electrodynamics is that they are linear partial differential equations. And they are linear in E and B. So what do I mean by that? So if you look at these equations, the 4 vector equations, then there is no E square or B square or E cube or B cube term over there. Everywhere E and B comes at its first order. Well, this is not essentially true if you try to write down the Maxwell's equations in nonlinear medium. Now, Maxwell's equations inside a medium, what we write down in terms of D and H, are fundamentally different than these Maxwell's equations. Why is that? So that we will come to later. But these equations, as we said, is applicable everywhere, even inside a medium. They are linear in E and B. And what is the advantage of that? The advantage is that we can solve this equation, we can use superposition principle to solve these equations. What do I mean by that? Well, if I have same boundary conditions, and say I solve, so I have rho and j given to me, and I write rho equals some rho 1 plus rho 2, and say j equals some j1 plus j2. Okay. When I write that, I get out of rho 1 and j1, I put in the Maxwell's equation the boundary condition that I have, and for source rho 1 and j1, and I get solutions which are E1, B1. And then I put in my Maxwell's equations rho 2 and j2 with the same boundary conditions, and I get solutions E2 and B2. Okay. Now, the solution for rho and j as the sources will be E1 plus E2 and B1 plus B2. And this, it may sound that this is very simple thing, but this is something that actually let us solve the Maxwell's equations using a very nice trick, and that we learn starting from the next day. But keep this in mind, that I can break my sources into small terms, and I can solve for each of them separately. And that's a big advantage that one gets because of the fact that the Maxwell's equations are linear. Nice. Okay, so let us discuss here a little bit about what happens inside a medium. Because there you may have a nonlinear medium, and this nice property doesn't hold anymore. Inside a medium, you write the Maxwell's equation. I'm not going to write them here, but you write in terms of D and H. And then you have to also write D in terms of E and H in terms of B. So once I give all of these to you, you will be able to solve for the Maxwell's equations. Now it turns out, or you must have already learned, that these quantities D and H are not fields, they are volume average quantities. What do I mean by that? Well, to get what happens inside a medium in presence of electric field and magnetic field, you don't really ask the question that what is happening, what is the electric field here and the magnetic field here at a given point in the medium. You ask the question, what is the average electric field inside in a volume around that point? And that average electric field is better described in terms of electric field, and the magnetic fields are better described in terms of D and H than E and B, because some properties of the medium gets added to E and B. Okay, so that we will discuss little more further in later in the course, but I just wanted to point you with this fact that when you write down the Maxwell's equations in terms of D and H, they are fundamentally different because you are writing it down in terms of some volume average quantities. So here, when I say that E and B are the electric field at that point X and B is the magnetic field at that point X, when I write H as a function of X, that H is not at that point, but the value of H is a value which is averaged around that point. So they are fundamentally different that way. Okay, so that's completes the discussion on the second point. For the third point, this may surprise you that we have these two parameters, epsilon naught and mu naught. What we can measure is a combination of them. Is essentially 1 by epsilon naught times mu naught, which we know, I guess you have done enough electrodynamics to know that this is speed of light square. So the measurable quantities is epsilon naught times mu naught. So this has a dimension of LT minus 2, which is the dimension of the speed. So epsilon naught times mu naught has a dimension of L2T, L minus 2T2, and that's what you can measure. These quantities separately cannot be measured. Well, that doesn't mean that you cannot measure the relative permeability and the relative permittivities. They can be measured, obviously, because they are the ratio of certain things. But what we call the free space permittivity and permeability, they cannot be measured. And this should not be very surprising, though it sounds when you hear for the first time. But if you think, what is the value of mu 0? So let me write in SI unit. So I am not writing farad meters, etc. The value of mu 0 in SI unit is 4 pi into 10 to the minus 7. What the hell pi is doing here? Why it is 4 pi into 10 to the minus 7? Pi is the ratio of the circumference to the diameter. Well, the value of this is 4 pi into 10 to the minus 7 because we have chosen it so. Now that's completely arbitrary choice. If you take this value 10 to the minus 7, and if you do not know already, C, the value of C is fixed in SI unit. Meter per second, obviously. If I use this 2 and epsilon naught mu naught is C to the power minus 2, that gives you a value of epsilon naught, which looks very surprising. But that's just our choice of mu naught. So if I choose my mu naught to be this and C is taken to be this value, this is a fundamental constant, this is fixed, there is no error on this, this is C is taken to be this value, then you get epsilon naught, which is this. You can just try to do the math and get the value of epsilon naught. So these values you cannot measure because this is something that fixes, this choice fixes unit of charge. Okay. So once you have chosen mu naught to be this, you get the value of the charge and you get a value of epsilon naught. So now you can think about it. You will see certainly that it is not possible to measure unless you give them a value. Okay. So this may sound surprising when you hear it for the first time, but nevertheless it is true. If you look at these equations, the Maxwell's equations, the 4 Maxwell's equations, let's ask the question, what this equation cannot describe? Well, they cannot describe a lot of things that we see in our everyday life, and that's the natural magnetism. Maxwell's equations cannot describe para, dia, ferro, etc. magnetism. All these natural magnetism that we see are quantum phenomena. They cannot be described using any classical phenomena. Now you may be thinking that, well, we had this old school description of an electron going around a proton, and that gives a current carrying loop. And I may be able to use that with Ampere's law to get atomic magnetism. You probably have seen in books it's being described like this. Now this doesn't work, and it is not that I am telling you for the first time that it doesn't work. It was shown by Niels Bohr in 1911, and in 1919, that this simple description of atomic magnets cannot give rise to any of the para, ferro, or diamagnetism, antiferromagnetism, anything, any of the atomic magnetism. Why is that? Because it's a problem. It's a problem of statistical mechanics. You may have one magnet giving rise to one atom giving rise to some type of atomic magnet, though this entire consideration of current carrying loop is itself is not doesn't work once you consider the quantum model of the atom. But even if I think for a moment that it works and one of these gives rise to one of the atomic magnets, then what happens is that in your bulk, in the material that in which you are trying to figure out what is the paramagnetism, say, there are many such atomic magnets which are completely randomly oriented, and when you calculate the average value of the magnetization, you will always find 0. And that's what Niels Bohr and Van Leeuwen showed. So classical electrodynamics, Maxwell's equations cannot explain para, dia, or ferromagnetism. So that should be very clear in your mind. I leave you for the time being for you to think about one more thing. So how many equations are there? Well, I have two divergences and they are scalar. So I have two equations there. And I have two curls, and curl is of a vector which gives rise to a vector. So I have 2 into 3, 6 equations there. So total I have 8 equations. But the variables to solve for are 6. The 3e and 3b, total 6. So how come I have 2 extra equations? Will they give me some unphysical constraints? Think about it. I will not give you the answer. The next point that we like to talk about is the fact that if I want to change from one inertial frame to the other inertial frame, what happens then? So I wrote reference frame, in bracket I write inertial, just to remind you that though I am changing the reference frame, these two reference frames are mutually inertial. They have their relative velocity is constant. And for this you need some preconceived ideas or preconceived knowledge, but I guess you have done. So say I had E and B, and this changed to E prime and B prime. I am not writing the transformations, but you probably know that E prime will depend on both E and B, and obviously on the relative velocity, so that I write capital V, and B prime will also depend on both E and B. Now this is something a little strange. V is the relative velocity. You should look at these formulas, how they transform. If you have not already done it in your previous courses, we will do it later in the course in more detail, and you will see it comes very naturally from something. But for the time being, we realize that to get to know E prime, I need to know both E and B in the other reference frame, and vice versa. Now this is strange. This is strange because we presume E and V as vectors. And if I do a coordinate transformation, which changing reference frame is a coordinate transformation, and if E and B are vectors, then I will expect expectations. E will, or E prime, which is the change thing, should be a function of E only, and can be a function of B. Similarly, B prime. This is not the reality. So your expectation is not the reality. And that is telling you something wrong is there in our understanding of the Maxwell's equations in this way, or understanding of electric and magnetic field in this way. And yes, there is something wrong. And what is wrong is that they're not strictly vector quantities. Okay. So if I do Lorentz transformations, or the transformation that takes me from one inertial frame to the other, E and B doesn't transfer as vectors. And this will be the root of formulating electrodynamics from a different perspective, and that we'll learn again in the second part of the course. And the last thing that I will discuss is in this form, if I am not trying to talk about Lorentz transformations, transforming to a different inertial reference frame, but rather just looking at the Maxwell's equations in whatever frame I have written them down and trying to solve this, I realize that there are two equations which are curl and two equations which are divergence. More or less, the structure of the equation is the following. So I have curl of E and divergence of E given. This, along with, I am given with curl of B and divergence of B. Now my curl of E terms has a B in it, and curl of B term have E in it, but nevertheless I have been given with, I have two vector fields and I know both curl and divergence of these two vector fields. The equations are coupled, so you cannot solve them separately, but I know the curl and the divergences. I also know the boundary conditions. And this tells us that I have unique solution for E and B. So it's not a single partial differential equation, which we already know is always have a unique solution given the boundary conditions. These are four different equations. They're coupled in E and B. But I am given with curl of both E and B and divergence of both E and B. with the boundary conditions. So that ensures that I have unique solutions of E and B. So this goes by the name of Meltons Theorem. If you really want to know more about it, you can look at the book Classical Electrodynamics by David Griffiths. In the appendix, they have discussed Meltons Theorem. Okay, so now, given this much background, let us see that how to solve the Maxwell's equations. Now, one thing is clear for us, that the mathematical description of E and B is not very clear. And we probably have already learned that there is a potential formalism of the theory. And that is what we'll discuss next. What is a potential formalism? It means that we seek for some functions, and these functions are what we call the potentials. That will give, that can be used to get E and B. And the clue is very clear. So how do I set these functions? Well, these functions can be scalar, these functions can be vectors, we really do not know. But to start with, we know that divergence of B equals to 0, and I use my knowledge of vector calculus. If divergence of any vector is 0, then there exists a vector, let us call this A, and you know why I am calling this A. When B can be written as curl of A. Why? Just because divergence of curl of any vector is 0. So immediately I get such a function, which now I can use to generate B. Or have I? I have got that B is given by curl of A, and so A is a vector and it works as a potential, so I call it a vector potential. But you see, curl is known, curl of A is known, but divergence of A is not known, it's not specified yet. So the vector potential is not fixed yet. That's what we learned from Meltons theorem, that both the divergence and curl has to be specified. Well, alright. So I've got one function, or three functions actually, three components of A. So A can be obviously function of both or all three x's and time. And you see that to get to this, I have used one of the homogeneous equations. So let us look at the other homogeneous equations. What does it tell us? The other homogeneous equation is curl of E equals minus del B del T, which I can write as curl of E, and B is curl of A, so I can club them together. You can write curl of E plus del A del T. Once I do that, I now realize that gradient, curl of a vector is zero, is the zero vector, means there exists a scalar function phi we call the function phi. It's a function of x and t again here, which or gradient of which is our vector. So this vector is the same as this vector. So from here I can write that E plus del A del T equals, I write it, so that's convention to write with a minus sign. Now this equation and the previous one, which is curl of A equals B, gives me, how do I get B out of A, and how do I get E out of now both phi and A. So given the scalar potentials and the vector potentials, I can now get the fields. You see, still remember that divergence of A is not fixed, and phi can have an additive constant. Phi can have an additive constant because only grad phi is appearing here. Well, of course, you immediately also recognize that A can also have an additive constant because only I am taking the derivatives of A. A constant which doesn't depend on either x or t. Now these two, we have these two relations, or writing down the electric fields and the magnetic fields in terms of the potentials, we have got using the two homogeneous equations. Let us try to see what happens if I use the inhomogeneous equations. These two, the homogeneous equations, has allowed us to define what is A and what is phi, and how do we get E and B from them. The inhomogeneous equation should tell us how we get A and phi in terms of J and rho, the sources, and obviously the boundary conditions. So let's start with the first Maxwell's equation. The first one that I have written down, there is nothing called first Maxwell's equation. The divergence of E equals rho by epsilon naught. So this is divergence of minus grad phi minus del T of divergence of A equals rho by epsilon naught. What I do here, this term is nothing but minus grad square phi. I add to it a term which is epsilon naught mu 0 del 2 phi del T2, and then in the right hand side I write the rest of it. So it is rho by epsilon naught. Remember, rho is also a function of all three x and t, and then I have del T of divergence of A from this term and from this term mu 0 epsilon naught del A del T. Remember, divergence of A is not fixed. It's written over here. Here, if you look at this, it's something epsilon naught mu naught del 2 del T2 minus grad square operating on phi. So we will write this as box square phi. So this is equals rho by epsilon naught plus del T of divergence of A plus mu naught epsilon naught del A del T. I'm sorry. So let me do the corrections here. So this is del phi del T, not del A del T. If it is del A del T, so this is everything is scalar. That would have been a scalar. So let me do the correction. Okay, so that is one of the inhomogeneous equation. The other inhomogeneous equation is curl of B, but curl of B is curl of, now B is curl of A, so curl of A, and curl of A is nothing but gradient of divergence of A minus Laplacian of A. So let us use that now. So gradient of divergence of A minus grad square A. What is there in the right hand side of that Maxwell's equation? I have mu 0 J and I have mu 0 epsilon naught del A del T, del E del T, and E is minus grad phi minus del A del T. So this is minus grad phi minus del A del T. You see, the second term is mu 0 epsilon naught del 2 del T2, and here I have grad square A. So these two again I can combine as box square phi, like box square. So here it becomes box square A. And what do I get in the right hand side? I get mu 0 J plus this and this combined, where I can take the gradient outside. Inside, what I am left with is divergence of A from that term. Well, that term has to be negative, so this should be negative. And from the other part, I have gradient of this term, which is also negative. So, but that is mu 0 epsilon naught del phi del t. Okay, so what have we got so far in terms of our potentials? We got that B, or let's write E first. E equals minus grad phi minus del A del t. We got B, which is curl of A, and we can write this together with the two inhomogeneous equations, which are box square phi is rho by epsilon naught plus del t of divergence of A plus, let me write 1 by c square for mu 0 epsilon naught that is the equation for phi. Similarly, I get an equation for J. Remember that divergence of A is still not fixed. And because divergence of A is still not fixed, I need to specify divergence of A to solve these equations. By the way, there are 4 equations here now. There are total 4 equations here. So I need to specify divergence of A. So now this is also the equations of classical electrodynamics. Okay. Now, divergence of A has to be specified from outside. Specifying divergence of A will fix A. Specifying divergence of A has a name. We call it fixing the gauge. See, what's happening here is that when the classical electrodynamics is written in terms of the scalar and the vector potentials, then there is a choice in this scalar and vector potential, which is what you choose for divergence of A. What is the scalar function divergence of A is, what scalar function it is. Depending on that, the solution for A will change, but I should choose that function in such a way that the solution for E and B cannot change. If the solution for E and B changes, then obviously I'll not get back the same electrodynamics. So let us ask the question, how do we choose A? So we need choices which keeps E and B unchanged. What do I mean? I mean that, so say A is changed to A prime. Okay. How can I do this change? To do this change, what I can do is I can add to a gradient of a scalar, any scalar function. I say I can do that. Why I can do that? Well, if I calculate divergence of A prime, that is now divergence of A plus, sorry, if I calculate curl of A prime, which is my B, which is my B prime, because A has changed to A prime, to calculate B prime, I have to do curl of that. So this is curl of A plus curl of gradient of lambda. But you know that curl of gradient of lambda is 0, that we discussed earlier. So this is just curl of A, which is B. So this transformation keeps B unchanged. So what happens to E if I add gradient of lambda to A? Well, E will change to E prime. So E will change to E prime. And E prime is nothing but minus gradient of phi prime, say. I'm presuming that phi also has to be changed to phi prime, and del A prime del T. Okay. So this is minus gradient of phi prime. I still don't know what is phi prime. But E has to be same as E prime. So E has to be same as E prime. So E, if I write here, it was gradient of phi minus del A del T. And in the primed case, this is del A prime del T, which is del A del T, and then gradient of del lambda del T. If we compare these two, you see that obviously these two are same, so they can be cancelled. I need phi prime to be same as phi minus del lambda del T. So if I change A and phi together, so if I get a solution, for the potential say the solutions are A and phi. Okay. Now I want to change them to A prime and phi prime. I can do that because I can change A to A prime and phi to phi prime and keep electric field and magnetic field the same. And that I can do by maintaining this condition and phi prime is phi minus del lambda del t. Okay. So this has to be maintained when I am changing from one A and phi to the other A and phi, which is essentially, as I said, is called fixing the gauge. So that gives you a degree of freedom of the field, because you can move around in that degree of freedom, just like you can move around in a degree of freedom of a dynamical system, which does not change the dynamics of the system. Here also I can move around, I can change my lambda in such a way that I can go from a phi to a prime phi prime to a double prime phi double prime, maintaining these relations. My actual dynamics, which depends on E and B only, that will not change. So this is called the gauge degree of freedom. It's an internal degree of freedom of the potentials. This doesn't appear if you try to write down the theory in terms of electric field and the magnetic fields. Now it turns out the description of the theory in terms of the potential is more mathematically correct, and because of that one has to care about the gauge degree of freedom. And it's the gauge degree of freedom which gives rise to many different things, which you will learn again later in the course. Now let us come back here where we said that divergence of A is not fixed, and it can be fixed in many different ways. But one automatic choice can be that divergence of A I just set to 0. So then what happens to the equations of phi and A? So choice. And this is particular choice, or all this class of choices are called Coulomb gauge. Its divergence of A is said to be 0. Okay, so it immediately gives a condition for lambda also. So you see that divergence of A said to be 0 means divergence of A prime is equals to divergence of A plus divergence of gradient of lambda. This is equals to 0, which says that for such a choice of gauge, your grad square lambda has to be 0. Okay. So if I am in a Coulomb gauge, so what does it mean? If I am in a Coulomb gauge, or if I want to go to one potential choice to another in Coulomb gauge, which means divergence of A is 0, then grad square lambda has to be 0. Grad square lambda, where lambda is the function which changes from one gauge to the other. Okay, what happens to these equations? Well, you can see that this divergence of A terms will disappear. So this will become grad square phi equals rho by epsilon naught and then Let's have a look. So I'll have divergence of A 0, but then I will have 1 by c square del 2 phi del T2. But you see, this also had a 1 by c square del 2 phi del T2 and a minus grad square phi. So combining the left hand side written this way, this cancels out. So what I get is the usual looking Poisson equation in an unusual form. Because now both phi and rho depends on x and t. What happened to the other equation, the equation of A? Well, let's have a look here. So I will have this term 0, but this term will remain as it is. So let's write that down. Grad square A equals mu 0 j minus 1 by c square del phi del t. Del phi gradient of del phi del t. Okay, so that's Coulomb gauge. The other choice is called Lorentz gauge. Here, it's very illuminating. If I look at these equations in this form here, what you do is you choose this form to be 0. That's the choice of the gauge. Divergence of A you choose to be minus 1 by c square del phi del t. So divergence of A plus 1 by c square del phi del t is chosen to be 0. And immediately you see that the equations now becomes of exactly same form. So grad square phi is rho by epsilon naught and grad square A equals mu 0 j. So in Cartesian, if I write them in Cartesian coordinates, four same equations. So they look exactly the same, 4 equations. Well, the details are different, but the equation, the mathematical structure of the equations, 4 equations, they are exactly same. In the previous case, this equation and this equation definitely have different mathematical structure. It's not so here. What else? Well, divergence of A I have chosen to be 1 by c square del phi del t. So if you try to figure out the same relation that I have got here, in this case, it will be different. So what will I get in this case? So divergence of A plus 1 by c square del phi del t is 0. So I leave to you to figure out what equation in lambda we get, says that if we know the solution for A and phi in one Lorentz gauge, what equation must lambda must satisfy says that I get the solution for A and phi in the other Lorentz gauges. Okay, so that's it for today. Starting from the next class, we will try to know how to solve such differential equations, such partial differential equations. Thank you.